Okay, so in the last lecture we have looked at various index structures, but then like the primary index, clustering index and the secondary index. But we found that modifying these indices is costly. So, if we have a dynamic file, then making use of these, effectively making use of these indexes becomes a little difficult. So, the index sequential access method files that we mentioned last lecture are most suitable for files that are relatively static. Here and there a few insertions and deletions might occur, but we will be able to handle them using overflow chains or deletion markers, etc. What if the file is actually truly dynamic? I mean, it keeps on. So, of course, we have also discussed how to manage that dynamic files using hashing. Okay. Now, in this lecture, I will focus on how to use B+Trees in order to take care of a dynamic file and then give search access to the records in the file. So, basically we are also talking about B+Trees. Okay. So, sometime after I explain this B+Trees, I will later towards the end of the lecture probably we will talk about the simple B-trees. Okay. So, but we are focusing largely on B+Trees. Now, you have studied tree structures as a very helpful data structure for searching through searching for an item in a given set of items. So, we have been familiar with binary searches, AVL trees for searching, and then you probably have studied red black trees or 2-3 trees, etc. So, the basic principles of tree based searching is the same here in B+Trees also, but one of the main things that you will find here is that what should be a node in the tree? What should be a node in the tree? A node in the tree in the memory thing was having some item and then depending on whether it is binary or 2-3 etc., a few pointers, right. But now the new consideration comes into picture here in the sense that the access of data from the disk is always in terms of blocks. So, when you read an unit, that is a block. So, it is about 4 kilobytes of data, right. So, we will want to treat that as a node and then there is so much space in that node, there is so much space in that node. So, how do we effectively utilize that space? So, basically what we do here, as you will notice a little while, in a short while, the number of children that a node has will be very high. We also call it as a fan out, The fan out will be very high, running to something like 100, 150 like that. So, a node will have 150 children. Now, if your fan out is high, then you can see that the first level you have 150 children, in the next level you have 150 times 150 nodes, in the third level you have 150, 150, 100 times 150 cube. So, if you sum it up, you can see that the structure can accommodate a huge number of nodes by just using 2 or 3 levels. Okay, so that is one great advantage of these structures. Now, okay, the B plus trees are designed as balanced trees. So, they are actually self balancing. We will show how exactly they balance, and these internal nodes will have some variable number of children. What I was talking about is the maximum, that the degree, the fan out is the maximum. Okay. So, we will see later on as to what are the other restrictions that are there. Now, one other thing is that all the leaves are at the same level, all the leaves are at the same level, okay, and the nodes are disk blocks. Now, in B plus trees, it is the leaf node entries that are there in the leaf node that actually point to the data records. So, the data records are actually in some other file in disk blocks. Okay. So, we keep a record, we keep a pointer to that data record in the B plus tree. Notice that we are talking of B plus tree is more like as an index structure. Okay. So, we will put the data records in a bunch of blocks and then keep the pointers to these data records in this tree structure. Okay. Now, all the data record pointers are going to be available only in the leaf nodes. I will tell you what is the advantage of this decision little later after explaining this B plus trees in full. Okay. Then the internal nodes, what will the internal nodes do? Internal nodes will carry index information, some information which will guide the search to go to the appropriate leaf level. So, unless you go to the leaf node, you will not get the pointer to the data record. Okay. And so, the internal nodes will have suitable information, so that the search will be guided to the appropriate leaf node. Okay. Now, the difference actually in compared to B plus trees and B trees is that the B trees, the internal nodes also carry data record pointers. We will come back to this point a little later. Okay. Now, broadly what these structures do, the B plus tree does, is to kind of make sure that all the nodes, I kind of interchangeably use the word node and block because the blocks are nodes. So, make sure that blocks are all at least half filled. I will show you in more detail about this point. Now, because all the leaf nodes are the ones that actually have the data record points, we have an additional feature in the tree saying that I can chain up the leaf nodes. The leaf nodes are at the last level, right. So, I will chain up these leaf nodes, and then that will provide in some sense a sequential access to all the data records in ascending order of the search key. See, if you take a binary search tree and then access the okay, not binary, yeah, we will adopt that idea. I will show you how leaf nodes are linked up a little later. Okay. So, let us come to the details of the structure. All the leaf nodes, remember that all the leaf nodes are going to be linked up as a list. Okay. So, now let us see, there is a notion of order, when the term order is used in order to indicate as to what is the maximum number of tree pointers that can be held in a node. So, for an internal node we define order M as the maximum number of tree pointers held in it. So, and if say 4 pointers are held in it, in order to guide the search you only need 3 keys. In a binary search tree you have 2 pointers, to search between to guide the search to either the left or the right, you need 1 key. If it is less than that key you will go left, if it is greater than that you go right. So, 1 key and 2 pointers. Okay. So, if you want to expand this further now, you keep two keys, then you can handle 3 subtrees. Okay. So, like that, so you will have m is the maximum number of tree pointers held in it, and m minus 1 will be the keys in the internal node. So, that is m stands for the number of points. Now, for the leaf nodes, the order is different. So, we write it as m leaf. M leaf of a leaf node is defined like this. The order of the leaf node is the maximum number of record pointers that are held in it. Record pointers that are held in it. And it is also, of course, the record pointers and the key or the value of the search attribute that has the value of the search field and the corresponding record. What do you mean by the corresponding record? The record has exactly that value for that particular attribute. Like for example, you are talking about roll number, right. So, that record has exactly this roll number. So, roll number and a pointer to the data record. So, for example, if you are organizing this index on roll numbers. Okay. Now, these are the orders. So, let me show you the Raghav, focus here. Let us look at the internal node structure. So, here is the internal node structure. It is a wide stuff here. The node will have huge number of keys, and if let us focus on smaller example here. Suppose it has 3 keys, then it will have 1, 2, 3, 4 pointers. Okay. So, all those records whose value for the search field is less than 2, x is less than 2, will be found in this subtree. All those records whose value is greater than 2, but less than or equal to 5 will be found in this subtree, and so on. Now, if you generalize this situation, you have P1, K1, P2, K2, etc. So, these K1, K2, Ki minus 1, Ki, these are all in sorted order. The keys are in sorted order. Okay. And then each of these P1, P2, these are tree pointers. They are in fact block pointers, because each pointer is a block pointer. So, this will point to a subtree in which all the you can find information about the records that have value of the search field x less than or equal to K1, which is the first key. So, between K1 and K2 you will find the in this subtree. So, Pi points to a subtree where you can find information about all the records whose search field values are strictly greater than Ki minus 1, but less than or equal to Ki. Okay. So, that is how we will organize these subtrees. And now, what is M? M is the maximum number of tree pointers that are there. So, this J is upper bounded by M, and interestingly it is also lower bounded by M by 2. So, it should be at least half full. This is to ensure that you have balance in the tree. So, it is at least half full and at most n number of tree pointers will be there. Okay. So, is this internal structure clear? The structure of the B plus tree internal node. Now, these keys are not giving you any pointer to the data record, okay, in which this particular value is present. They are not giving anything like that. They are only telling you that if the search field value is less than or equal to K1, go this side. If it is greater than K2, go this side, etc. That is all they are saying. So, they are guiding the search. The keys will guide the search. So, here is all that information. So, internal node of order m will have at least m by 2 number of pointers. We give an exception for the root node. The root node is allowed to have just 2 pointers. Root node is allowed to have 2 pointers, and it contains at most m pointers, and these are the 3 pointers. Say if it has P1 through Pj 3 pointers with K1 less than K2 strictly Kj minus 1 as the keys, then these are the this is how the subtrees are pointed. So, Pj points to records with key value x greater than this particular last key. Okay. So, this is clear. Let us proceed. So, this is very similar to the usual search trees, but the only issue here is that we have huge number of keys. Why is it that we have huge number of keys? Because we can afford to have, we have space there. When you access a unit from the disk, you always get a 4 kilobytes of data. So, if you have that much space and the keys are only some 20 bytes and things like that, I can afford to organize a huge number of pointers. That is the idea. So, let us now look at the leaf nodes. Leaf nodes have a slightly different structure. Okay. Leaf nodes are the ones that they do not have to point to any tree nodes, they are the last, right, you have reached the leaf. So, the leaf will now have pairs of things. What are the pairs? The key value and the pointer to the actual record in the disk blocks that will contain that is the record whose value is equal to this key, right. So, K1 PR1, K2 PR2, Kj PRj, and the restrictions are like this. It contains, okay, I told you that we are going to chain up these leaf nodes. So, it is going to have one pointer P which will point to the next leaf node to the right. There are a huge number of these leaf nodes. So, you start from the leftmost leaf node, then you will have a pointer to the next, pointer to the next, and then you can actually traverse through the leaf nodes starting from left to right. Okay, that is very interesting. Okay, it contains at least m leaf by 2 record pointers and at most m leaf by 2 and in the same number of key values. This is at least, right. And at most m leaf, this is what we have defined as the maximum pointers it can have. So, that is the order. So, at most m leaf record pointers and key values. And of course, the node the keys are ordered K1, K2, Kj, and then these are the record pointers. So, as I was indicated, Pri points to the record with Ki as its search field value for all of these things. So, the leaf node structure is clear. The only interesting only aspect that you have to remember is that the structure of the key leaf nodes is different from the structure of the internal nodes. Okay. So, that makes defining the node for the tree as a structure a little difficult. You will have to define leaves separately and internal nodes separately in the programs that manage this. Okay. So, now let us get some idea about what are these orders that we are talking about. Let us say block size B is given and the size of the index field is V. Then the size of the block pointer is about P, size of the record pointer is PR, all these are there. Then the order of the internal node basically is governed by this inequality. So, m times the block pointer plus m minus 1 keys will be there m tree pointers, m minus 1 keys. So, each key is of size v. So, this sum should be less than or equal to the block size. Basically, this is the inequality that can be used to fix m. Obviously, we will choose the maximum value that satisfies this inequality. In a similar way, for order of the leaf node, since there are at most m leaf record pointers and keys and one block pointer. So, you see m leaf times PR plus V and plus the block pointer, that size should be again less than or equal to P. So, this is the inequality that will govern the choice of m leaf. So, for some typical numbers like if you take actually half a kilobyte as a block size and the such key as 8 bytes and the other the pointers etc., then you can see that you can later check these values. M will be is about m is maximum 37. But a half a kilobyte is actually not a typical size for the block size, it will be something like 2 to 4 kilobytes. So, you can see that this will be actually pretty high. So, you can choose for some say 36 or 37 here and then go ahead. So, what you are saying here is that each internal node, the moment you retrieve it, you will get so many children. You can then search through and then find out the appropriate subtree to go down. The leaf node, in a similar way, you can substitute these values in this inequality, then you will find that m leaf is about 33. So, you can choose this 32 or 33 and then you can proceed to implement it. Now, this one will tell you usually the B+Trees will have about 3 or 4 as the height, because the fan out is so high, then you can handle reasonably big files with that. Now, notice one thing here, that nowhere we are using the size of the record itself. The size of the record is not being used at all. The records are in a separate place on the disk. We are only looking at a pointer to the record and the key value, such attribute value. Okay. So, here is an example B+Tree structure. I have taken some ridiculously low numbers to illustrate the points, bear with me for that, because in practice this will be not possible, they will be huge. So, let us take m leaf as 2, that means each leaf will have exactly at most 2 record pointers, and m is 3, that means each internal node will have maximum 3 children and a minimum of 2 children, because m by 2 is 1.5, take seal, it should have minimum of 2 children, maximum of 3 children. Okay, you can see that. So, it should be obvious now by now that these search field values will get actually repeated inside in the internal nodes, right. And each of these search field values need not appear, but some of them will appear here in the internal nodes, so that the search can be guided to the appropriate place. Now, you can see that this in the leaf, you can see that okay, in the diagram here what I have done is to put the key here and the pointer here to its left, right. Okay. And this is the pointer that I was talking about, which links up the leaf nodes. So, if you start at the leftmost leaf node and then simply access these records using these record pointers, then you will actually get all the data records in the increasing order of this particular field, in spite of whatever be the order in which they have been organized on the disk. Okay. So, this is what I was talking about as giving sequential access or sorted access to the data records based on this particular. Now, searching, of course, you will take the key and then go here and then check if it is less than equal to 3, then you go this side. If it is greater than 3, you go this side, etc. The usual search mechanism will be made use of. And then finally, when you reach here, you will get the record pointer, if it exists. Okay. If it exists, it is possible that, say for example, 5 is not existing here. Okay. So, is that clear? You have any questions on? Next, we will actually discuss how to handle insertions into this structure and how the structure evolves as we insert and actually delete records. Okay. So, insertion into B+Trees. Now, a key and record pointer is what we get. By key I mean the value of that search attribute. That is what key is. A key and a record pointer is what we get as input, and you are supposed to insert that into the B+tree appropriately. Is that clear? Now, obviously, in order to insert this, you have to first search for the appropriate place to insert it. That means you will take this key and then go to the appropriate leaf where it is supposed to be present. And we will assume that this particular key is not present right now. If it is present, then there is no question of inserting, right. So, let us make an assumption that it is not present. So, you go to the appropriate leaf node by using the usual search mechanism and then insert it there. Okay. Now, various issues will come. If there is no problem in the leaf, in the sense that leaf is not full, then we can simply insert the new key record, new pair, the key and record pointer into the leaf and then be done with that. What if there are other, so if the leaf node has some upper bound on the number of record pointers it can hold. Okay. So, suppose it overflows, it already has huge number of record pointers, now you are inserting one more, so there is a overflow. So, when there is a overflow, what we do is take that leaf, simply kind of cut it into half. So, node is split at a j. So, how is j is m leaf plus 1 by 2. So, simply to get a appropriate number. So, you might question what is sacrosanct about this, why can't I take seal and things like that, I mean floor and things like that. But let us stick to one set of formulas for this. You are getting roughly a number in the middle. Okay. So, m leaf plus 1 by 2 either floor or seal will give you the middle number. So, we will take this seal for uniformity sake, let us all follow this thing. So, node is split at j and the first j entries are kept in the original node, okay, and then all the entities from j plus 1 onwards are moved to a new leaf node. Now, this new leaf node has to be accommodated into the structure. Okay. So, jth key value, the kj, is going to be replicated in the parent of that particular leaf node. So, you try to now insert this kj key into the parent of the original node that you are splitting. So, I will show you with an example now. Now, we will come back to this case. It is also possible that while you are trying to insert these keys into the internal nodes, the internal node might also overflow. If there is enough space in the internal node, then you are creating a new subtree in the internal node. But if internal node has already sufficient number of subtrees, then the internal node will also have to be split. Okay, so we roughly follow this same kind of a policy for that. The node is split at m+1/2 floor here in this case, and the values and pointers up to that particular Pj are going to be kept in the original node, and you can see that in this case the key Kj has to be actually moved, not to be replicated, it has to be moved to the parent of the internal node. Okay, so I will illustrate this with examples now. We may come back to this slide if necessary. Okay, here is a series of these insertions. So this is a bit of a complex slide. It has 4 pictures on it, so follow it carefully. So the pictures are numbered 1, 2, 3, 4. So we start off with an empty structure which has just and then we try to insert 20 and 11 into that. And remember that m is 3 and m leaf is 2. That means we can only have 2 record pointers. So this is the, so if there are just 2 records, then you have just 1 leaf. Now you try to insert 14 into this. So the appropriate place for is 11, 14 and 20, and there is no space here. So now I have to split it. So I will split it in middle. So middle is m leaf +1/2, which is 2. Okay. So I keep 11, 14 here and 20 in the new leaf, and then move this 14, which is this Kj, and make a new node. This is the parent of this particular leaf. It did not have parent, so now we are creating a parent, and then insert this 14 in the parent node, and then set the appropriate 3 pointers. So now you can see the 14 will start guiding the search. If it is less than or equal to 14, you come here. If it is greater than 14, you go there. Okay. So leaf nodes, if it is split, then we take the middle key, and then if it has a parent, we will try to insert it into the parent. If the node does not have a parent, we will create a parent and insert this 14 into that, and then set the 3 pointers appropriately. Now let us see in this structure. In this structure now, we will try to insert one more record. Let us try to insert 25. So you can see that you come to the root and then check that 25 is greater than 14. So you go to this place. Then fortunately there is space here because it can hold up to 2, right. So you go and simply insert it there. So you insert it at leaf node. So no problem in this. Now try to insert 30. So obviously in this case the search will guide to this leaf node, and you are supposed to insert it here 20, 25, 30, but then this has to be split. So you split it. So into 20, 25 and 30, create a new leaf node, and they take this 25 and replicate it to the parent. The parent already exists, so you will go and insert this 25 into the appropriate order, in appropriate order, and then set the new pointer to the new leaf. Okay, pointer to the new leaf. So when you take 25, so 20, less than or equal to 25 are supposed to be there here, right. So setting this 25 here, fits our policy. Putting this new leaf, which is new key, and putting it in the parent appropriately will keep our policy, that the subtree will have keys which are less than or equal to this. And the new leaf has been created. So, this 25 and the pointer to the new leaf will be passed up. So, when you insert 25 to its right, you will insert this key, this pointer. So, that will take care of this new leaf. Okay, that is how insertion takes place. Of course, I am not giving you very detailed pseudocode for insertions, but I want to give you an idea about how insertions and deletions take place in B+Trees. Okay. Now, let us see to this structure, try to remember this, okay, 14, 25 like this. So, now we try to insert 12, try to insert 12. So, 12, if you try to insert 12, it is less than 14. So, it should come here. So, this should come as 11, 12, 14, right, and so this cannot accommodate 3. So, it has to be split, and if you split, then there will be 1, 2, 3, 4 keys, 4 leaves, and any internal node cannot handle 4 leaves, it can maximum handle 3 children. So, this node has to be split now, okay, this node has to be split. So, this will be first split. So, 11, 12 and then a separate leaf with 14 will come into picture. Okay. So, there are now 4 leaves 11, 12, 14, 20, 25 and 30. These are the 4 leaves that comes in picture. Now, this 12 you try to insert here, try to insert here. So, it comes as 12, 14, 25 it comes, but then it cannot accommodate. So, what this will be split. When you split this, 12, 14 will go into one node and 25 will go into the other node. Okay. Now, but in this case, what exactly happens is that the middle key 14 is actually moved up. The middle key, since it cannot accommodate 3 keys, we will find the middle key and then move it up. And since there is no parent for this, no parent will be created and then 14 will be inserted here and the left will come here, right will come here. Okay. So, this is a new, so the whole structure has gained height now. We have a new root node, we have a new root node. So, the split at leaf level triggers overflow at the internal node and that split again that triggers a split at the internal node, and when you split an internal node, the middle key will be actually moved to a new level and then the pointers will be set up accordingly. So, remember this 14 has to be moved up. There is no question of replicating because in the internal nodes there is no replication of keys. So, we will move it up and then set the pointers again. Good. So, this is how the structure can gain height as it evolves. Now, try to insert 22 into this, insert 22 into this. So, sorry, insert 22 into this, it will 22 is greater than 14. So, you come here and then 22 is less than 25. So, you come here, you try to insert here and then the usual policy 20, 22, 25. So, and then 2 leaves will be created and then 22 will be moved up. So, there is space here. So, 22 will come here. So, let us see the structure. So, 20, 22 will come here, 22 is replicated up and then this new point, the pointers will get adjusted appropriately. Now, try to in this, let us try to insert 23 and 24. 23 will come here, luckily there is space here. So, you can simply insert it here. When you now try to insert 24, again that also tries to come here. So, there will be again split here. So, that will cause actually a split of the internal node, because a new 4 leaves have come into picture. So, that will create a split here. So, you will now see that that split will not propagate further. So, 22, 25 are created. The middle one 24, which we are trying to insert, is actually moved up, and then an appropriate it is put at an appropriate place, so that this search can be guided to the appropriate subtree element. Now, you can see that 24 is the maximum value in the subtree that is pointed to by this particular pointer. So, that property is kept as it is. Okay. So, study these insertions carefully. There is a you will find detailed pseudo codes for these insertion algorithms. Now, deletion has to be also handled. So, to delete the entry, so supposing you get a delete request, then obviously you should first locate it as to where it is in the leaf, and then delete it from the leaf. Okay. Delete the entry if it is present in the internal node also, and replace it with the entry to its right or the right sibling. We will see how exactly it is. So, so underflows can occur actually while you are deleting, underflows can occur, in which case we actually redistribute the keys. So, we will try to borrow keys from the left sibling, and if it is not possible, borrow keys from the right sibling. If it is still not possible, we will merge the nodes. The details I am skipping, but let me show you some examples. So, let us say we have this kind of a B tree, B+tree. Let us various 20 is here. So, we are trying to delete 20. So, in this case we will go to the appropriate leaf and simply wipe out 20, and the record pointer will be deleted, but fortunately this has another key. So, nothing no underflow occurs here. So, we can simply retain this leaf as it is. So, the structure does not change much. So, 22, 23, 24 etc. the whole thing will be as it is. Now, let us take this and then try to delete 22. Okay, in this structure, let us try to delete 22. If you delete 22, then this leaf itself goes. So, if this leaf goes, then what is the point having this, because it loses one child. So, it cannot have less than that many number of children, less than 2. So, something has to be done about this. So, what we can do is to minimize the changes to the tree, what we can do is, instead of removing this leaf, we can actually try and look at the left sibling, this sibling, right sibling here, right sibling, and then borrow a key from there. Suppose you borrow a key from there, then I can retain this key, leaf as it is. Okay. And I do not have to do any much changes. Of course, since 22 has gone now, so I should replace it by whatever I have borrowed. See, I can borrow 23 from here and then replace this 22 by 23, then everything will be alright. Okay. So, that is what we do when, so try to minimize the changes to the tree. So, borrow a key from the right sibling and adjust it. So, this is how we have done that. So, 22 is removed from the leaf, internal node entries from the right sibling are distributed to the left. So, and then this pointer, this of course, if you change this, then you should change this also, because this should be the maximum in the subtree. Now, let us see what happens if you try to delete 24, then there is no chance of these people helping each other. So, in this structure, let us delete 24 and then what exactly happens. So, if you delete 24, then this fellow does not have a this leaf cannot borrow from 23, because that already has only one record. So, basically now this and this have to be matched. this internal node and that internal node. So basically when you have deleted 24, then this particular internal node has only one leaf, which is not allowed. So what these two people do will collaborate and then redistribute the subtrees among them, So if they cannot do, they will simply merge. So they will merge into one tree and then take care of the subtrees. So 23, 25, 30 are the 3 subtrees to be taken care. So we will simply merge these two. We will merge these two and then not disturb the tree beyond that. Because of course, this 24 has to be deleted because 24 has been deleted. So now merge these two and then retain the pointer as it is, then the search will be appropriately guided. So greater than 14 will come here and 24 is not in the picture. So like this we can basically follow the policy of borrowing from the siblings or cooperating with the siblings in either taking their subtrees or merging the subtrees together. So let's take delete 14 here. So in this the root has 14, let's try to delete 14. So 14 is here. So if I delete 14, then fortunately its sibling has 2 keys. So I can borrow 1 key from here. So if I borrow, then this will change. If this changes, it also has to change. So this is how, so you can change it appropriately, keep the structure but then change the values. Now if you try to delete 12 in this structure, then there is really no scope. So actually you can see that there will be a level drop. The root will itself go and then the new root will come into picture. So if you delete 12 now, this fellow will have only one child, which is not allowed, okay. And now you try to merge it. If you try to merge it, then this fellow will have only one, which is not allowed. So then basically you will have to drop this parent and then adopt this as the new parent and then adjust the tree again. So this is how the B+Tree can actually lose height as it goes. Okay. So with this I have given you an idea how B+Trees will help us in organizing a dynamic file, and they can expand and shrink, and then they will give 2 kinds of accesses. On the search key it will give you a quick access. What is the quick? How quick you can get? It is the height of the structure, that many number of block accesses you have to do, and that is same for all keys, you can remember, because all the leaves are at the same level. Okay. So you will get quick access to a record, and if you traverse from the left to right on the leaf level, then you will get access to all the records in the increasing order of that particular search field value. So these are the 2 things that you can do. Only one issue with the B+Trees is that all the accesses have to go through the root. The root block of the structure is the most sought after thing. Everybody has to start their search through the root. So the root becomes in some sense a most sought after node block, and kind of becomes a hotspot, because we will later on see that if you want to change anything, you have to lock things. So if you lock it, then nobody else will access it. So there will be a lot of issues. So it becomes a hotspot. So that is the only disadvantage with B+Trees. Okay, so we will stop here for today, and I will see you tomorrow evening.